Hey guys, in this tutorial we are going to learn about the inode number in Linux. In the last video we saw that whenever we use option I with ls command, then we will display a number, and that number is called as the inode number. So basically what is basically use of inode number? So an inode number in Linux represents an inode in Linux. And what is the use of this inode? So to understand that, uh, we should understand that Linux stores everything in a file system, or we can say Linux follows a hierarchical file system as we have already discussed, and then everything is arranged in files in Linux. These files in memory are stored as inode, or we can say in storage area. These file names are actually stored as inodes, and the file names are the pointers to these inodes. So we have a file system, those contain the file name, then we have these file names which are actually pointing to inode numbers, and these inode numbers are containing the information about the actual data in Linux. So if I go by definition, then inode is a data structure which holds the metadata about your stored data. So if we talk about the structure of inode in Linux, then we have, in case of an inode for a directory, we have a simple data structure that contains the information about the files along with the inode number and the length of the file. And in case of file, however, the structure of an inode is little bit typical, and it contains the following information. So for this, let me first show you an example, and you can see here that for a file we have several information available, like the permission, then we have the user and owner, and then the timestamp at which it was created, and finally the date and the size. So all this information for a file is stored in an inode, and it somewhat it is somewhat like this, that it contains the mode, then owner, size, timestamp, and then for storing the data, or for storing the information about the data which a file is containing, it has direct blocks and 3 indirect blocks, which are called as first indirect block, double indirect block, and triple indirection block. So what does they mean? We will take it later. But before before getting into that discussion, we should understand what is a block size. So a block size is a minimum size which a file will occupy in the storage. So let me show an example. So here, if I want to know what is the block size of this file system, so block size is basically the minimum amount of space which will be occupied by a file. So let me create one file of 1 byte and store it inside a file A. So if I do du, that is the disk usage of this file, then you will see du-h of A, or you can do like this, du-h of A. Then you can see it has occupied a space of 4 KB, but it was just holding a single character, that is 1 byte. So you can see that instead of having a 1 byte inside it, it is holding or occupying a space of 4K. So this is the minimum space which will be occupied by a file, and that is the block size which we are talking about. So here we know how we can find the block size. So if we go further in the structure of inode, we are saying that in an inode we have several parameters related to a file, or we can say attributes related to a file, and then we have 12 direct data blocks in an inode. So if I say that what will be a size of a file which an inode can represent if it has only 12 direct blocks. So here I will say that it can represent a file size of 48K. And why is that dependency? Because if I have a file say A and it has an inode, suppose this inode, then the representation will be like this. In the inode block area, we will have a inode assigned to it, suppose inode 1, and it will occupy a 12 block structure in data block area, which is again in our hard disk. And if I want to represent a 13th data block here, then I will require one more inode, which is not possible. So I hope it is clear. Let me copy this. So let's suppose this is my 12th data block. So what do I mean here is, if I want to represent this 13th data block using the same inode, then it is not possible, because we have, as we said, we have only 12 direct blocks inside this inode. So if I want this data block to be pointed, I will have to use another inode number. That is not possible if we have only 12 direct blocks in a inode. So to overcome that, to overcome this problem, we have indirect blocks, and the first indirect block says that you can represent another data blocks using this indirect block. So this indirect block will represent the next data blocks for you. So what do I mean by this is that this will be an indirect block, this will be there will be a indirect block, so this is indirect block, and it will be lying just next to the 12 data blocks which we had, and this will be containing the information of next data blocks. So let me say it was block 13, and then we had one more, and so on, which will be again pointed by this indirect block. So if I have a block size of 4K and one block pointer say takes 4K of 4 bytes of space, then we have, by calculation, if a block size is of 4K and the block pointer size is 4 bytes, then how many then we will have how many block size or blocks this block pointer can point to. It will be 4K divided by 4 bytes, and it is 1024 new blocks can be pointed. I hope this is clear. So now if I say that I have 12 direct blocks and one indirect block, or one single indirect block, which is the first indirect block, so how many or how what will be the minimum, or sorry, maximum file size which this block can represent? So it will be, sorry, as in the earlier case we had 12 into 4k. Now it will be 12, sorry, due to some alignment I will have to write it here itself. So let me make some here. So now what we have 12 direct blocks, and they are giving me a space of 4k. And now we have one indirect block that is pointing to 1024 direct blocks. Let me write it inside this bracket. One indirect block is giving me a size of 1024, sorry, one indirect block is giving me 1024 data blocks, and 1024 data blocks will give me a size of 1024 into 4k, that is equals to how much? 1 MB, and plus the earlier we had 48k. So now the file size which we can represent using this structure is 1 MB plus 1 MB plus 48 KB. So it will be around 1.42 MB, sorry, 1.48 MB. So in the similar fashion we have the double indirection block which will represent a single indirection block, and those single indirection block will be representing. So here you have seen that one direct block was representing the direct blocks. Now if I talk about, and this is from here, this was the first indirect block, and if I talk about this, Control C, Control V, if I talk about the double indirect block, sorry, it was from not from here, it was from here, that we have a double indirect block, double indirect block, and this is itself is representing, see, Control E, this itself is representing 1024 indirect single indirect blocks. What is happening to this? So here we have a double indirection block which will represent in the similar fashion as a single indirect block was doing. It will represent 1024 indirect blocks, and those 1024 indirect blocks will in return will be pointing to again the single indirect blocks, 1024 single indirect blocks. So here it will again increase our calculation by, if I talk about the size, then again we can add here 1024 into 1024, and that will come out to be around 4 GB of space. If we have a single indirect block and a double indirect block along with a 12 indirect block, then the file size which we can have is 4 GB plus 1 MB plus 48 KB. So this is how it is. This is how we can calculate a size limit of a file in Linux. So if I talk about the triple indirection block, then the same logic will follow, and this inode, this triple indirection block will represent in triple indirect block in data storage data block area, and that triple indirect block will be representing double indirect blocks 1024 double indirect blocks, and those double indirect blocks will in turn will represent single 1024, when single double indirect block will in return will point to 1024 single indirection blocks, and so on. And then this file size will become around 1 TB. So in Linux we have 4 TB. So in Linux we have a maximum file size restriction of 4 TB if the block size is of 4K and the block pointer size is of 4 bytes. So this is how we have the file system limitation, file size limitation in Linux. So I hope I have made clear what is inode and what is the information which is stored inside inode, and how we can calculate that what is the maximum size of file that can be stored in any file system. So we are clear here. Then we have explained this as well. Then we have got to know and how we can find the block size in Linux. So that is all I think we have. So the key takeaways in this tutorial, what were our key takeaways? So the first thing which we learned is what is inode number. Then we learned what is maximum file size, or we can say how to find maximum file size in Linux. And then we had calculations related to structure of inode. And then we have few questions in our mind that what if now we have few questions in our mind that what if the inode numbers get exhausted, so what will happen in that case? So the answer is very simple. If we have this inode numbers got finished, then even if we have a space in data block area or in our storage space, we will not be able to say it. So how are we going to find it? So how to find the inode consumption in our file system? So let me show you a practical for this. So here if I do df-h, then it will show that we have used 10%. Let me take an example of root. So we have used 10% of it, and the available size of this root disk is 404 gigabytes, and we have used 41 GB of it. So now I want to see the same information, but now at this time what we have done is we have used option I. So in this case it is showing the information about the inodes. So in case of root we have total of these inodes free, and we have used 2% of the inodes, and these many inodes are free for me to be used. So what will happen if our inode numbers get exhausted? So in that case, even if there will be a space available like this, even if there is a storage space available, then also we will not be able to use it, because there will be no inode number pointing to those storage blocks or the data blocks. So we have got to know that how we can find out the inode consumption in our file system. And what if inode, what if we want to increase our inode numbers? So for that we will have to, for this what we have to do is we will have to again create our file system, and we will have to allocate the file inode numbers accordingly. If we want a larger number of inode numbers in our file system. So these are all the points which we have discussed, and I hope you would have liked this lecture. And please do like and subscribe if you want to get more interesting videos further. Thank you.